Okay, so welcome back. Today we're going to begin taking a look at Chapter 9. In Section 9.1, we're going to take a look at some more hypothesis testing. But this time the hypothesis testing we're going to take a look at is going to be two-proportion hypothesis testing. Now, what does that mean? Well, in Chapter 8, we did one proportion. Someone made a claim about a proportion. We gathered one set of data, and we tested that one set of data against that claim in the equality statement in the null hypothesis, but against the claim essentially. In this section, there are going to be two populations, and there's going to be a single proportion, a single measure that is going to be created, or we're going to be tested against both. And so we're going to be testing a claim against that. So essentially what's going to happen is someone is going to make a claim that the proportion, let me try that again. Someone is going to make a claim that the proportion of population 1 is maybe the same as population 2, and then we'll test if they're equal. Or they'll say proportion 1 is less than proportion 2. So then we'll test the claim about this one being lower than that one, or higher than that one. But essentially there's going to be two populations. We're going to measure the same thing in both populations, come up with that proportion, and that's what we're going to test. Right? When we're talking about probabilities or decimals or percents, all of that's going to fall into the idea of proportions, right? So we're going to run a hypothesis test about two population proportions. Because of that, we're going to have all sorts of crazy notation floating around, right? There are two populations, population 1 and population 2. Okay? Everything about population 1 gets a subscript 1. Everything about population 2 gets a subscript 2. So N1 is the sample size for population 1. X1 is the number of successes in sample 1. P hat 1 is X1 divided by N1. Q hat 1 is 1 minus P hat 1. And all of those are statements about population 1. N sub 2 is going to be the sample size for 2. X sub 2 is the successes for 2. P hat 2 is X2 divided by N2, sample 2 proportion. Q hat 2 is going to be the complement of P hat 2. The only time that we commingle our sample data is when we calculate these two things right here, which are the P means and the Q means. I remember we put a bar over top of something, we say the mean of that. So P with a bar over it, P bar, is going to be the mean of the P's, and Q bar is going to be the complement. Right? The requirements for this is, of course, we need to have random sampling, but that's always requirements. Now it's just two random samples because there's two data sets to compare the two populations. They have to be independent, those two samples. Right? Remember, independence means that this one doesn't affect that one. They're not paired somehow or matched. Right? And for the two samples, that 5 successes and 5 failures must be true. That is N1, P1, N1, Q1, N2, P2, and N2, Q2 all must be greater than or equal to 5 for this to work. Okay, so at least 5 successes and 5 failures for everything. Okay? Now, the math behind the scenes is still math that turns all of this sample data into a z-score on a standard normal distribution, and then the p-value will be the probability of that score or more extreme. Okay? So a left tail for more extreme if we're looking for lowers, a right tail for more extreme if we're looking for highers, or an appropriate tail if we're looking at a two-tailed distribution. How is that z-score found? Well, essentially, this is the difference between the two samples. This is the difference between the two populations. When I subtract one from the other, essentially I'm getting like an x in my numerator. Right? And then downstairs, this business with this root here is essentially finding a version of a standard deviation. And when I take an x divided by a standard deviation, I get a sampling distribution value z. That's the math that's happening. Right? We're never going to use this formula. We are never going to calculate any of this business by hand. There's no reason to, okay? But in case you're wondering what's happening, that's the math that's behind the scenes. Okay? All right, let's look at an example, see if we can put all of the stuff into play and see if we can figure out what's going on here. All right. So here I got my first example. A study of 200 randomly selected occupants in passenger cars and 250 randomly selected occupants in pickup trucks shows that, and I'm going to stop right there because I want to talk about what's already been said. When I read that, and hopefully you're reading along with me, did you see the two populations? One of our populations is going to be people in cars, and one of our populations is going to be the people in the pickup trucks. Those are our two populations. This 200 that's right here, and this 250 that's right there, those are going to be our samples, right? All right, so the first thing I have to do is I have to, in my mind, come up with who's one and who's two, who's population one and who's population two. Now, I've always done it personally as whatever one shows up first in the problem is one, and then the other one's two. So I'm going to call this group one and this group two. All right, so let's go back and start again. So a study of 200 randomly selected occupants in passenger cars and 250 randomly selected occupants in pickup trucks shows that 91% of the occupants in passenger cars and 83.2% of the occupants in pickup trucks wear seatbelts. Okay, I got a lot of information there. Do you see that these two numbers now are hats? That the 91 is a sample proportion for group one passenger cars, so that's P hat 1. And that the 83.2 is a sample proportion for group 2, so that's P hat 2. All right, I'm going to pick back up at the at. At a significance level of alpha equals 0.10, can you reject the claim, so here's my claim showing up, that the proportion of occupants who wear seatbelts is the same for passenger cars and trucks? So there's my claim. My claim is literally that cars and trucks are the same when it comes to wearing seatbelts. Or, mathematically, that P1 is equal to P2. The proportion from population 1 passenger cars is equal to the proportion for population 2 pickup trucks. Right? I need to turn that claim into a pair of hypotheses, a null and an alternate. Right? Now, since this is a two-sample test, my null and my alternate are both going to be statements about P's. Right? So in this case, since our claim contains equality, that's going to be the null. That is that P1 is equal to P2, and then our alternate will be that P1 is not equal to P2. So our claim is the null, our alternate is this complement, and now I need some data. So I'm going to go back to the problem and start looking for data. Right? I've got an N1. My N1 is 200. The sample size from group 1, which we call passenger cars, 200. I've also got a P hat 1. That's the proportion from group 1, which is our 91%, 91.0. Right? I've got an N2. That was the sample size for group 2, which is 250, the 250 occupants and pickup trucks. I've got a P hat for group 2, which is the 83.2%. I also have an alpha level of 0.10. Okay? Now, I'm not sure if that's all the data I need or not, so I'm going to go ahead and check. Right? So I'm going to look at the test that I need to run. The test that I need to run is going to be a two proportion Z test. I have two proportions that I'm testing. The math behind the scenes is a Z test. So I'll punch that up, and yep, just as I feared. Just like the one prop, the test doesn't care about P hats. The test needs X's. Right? So how am I going to get an X1 and an X2? Well, the same way I got them before. I remember that p hat was x divided by n, and whether I put subscripts 1 everywhere or subscript 2 everywhere, that formula still holds. So I can find my x1 by just taking my n1 and multiplying it by my p hat for group 1, and I get that this is going to be 182. And I can find my x2 by doing essentially the same thing with 250 times 0.832. And that gives me 208. Now I do want to point out something. In this example, both of our x's worked out to be whole numbers. If either of them had come out to be a decimal, I would then just round appropriately to get it to be a whole number. Okay, so now I'm going to go back and run my test. This is a 2-prop z-test. My x1 is 182. My n1 is 200. My x2 is 208. My n2 is 250. The alternate is a not equal to, so I'll select that first one, and I'll go ahead and calculate. And I got that my test statistic, should I need that, is that z there at 2.418677324, round wherever they tell me to round it. But more importantly, I've got a p-value. My p-value is 0.016. Okay? Now when I compare my p-value to my alpha, I see that p is much smaller than alpha, which means we should reject that null hypothesis. Maybe you've got that table memorized by now, maybe you don't. If you don't, go ahead and look back at it, but if you do, that's fine. I'm rejecting the null hypothesis. The claim was the null hypothesis, so that means that there's sufficient evidence to reject the claim, or there is enough evidence to reject the claim. The two proportions are equal. Now, of course, with all of these, you could fluff that up as much as you wanted. You could say there is enough evidence to reject the claim that the proportion of passengers in passenger cars and the proportion of passengers in pickup trucks that wear their seatbelts is the same at a significance level of 0.10. That's a lot more words to say the same thing. Right? All right, so let's take a look at what happened here. Somebody made a claim that these two things were the same. The proportion of passenger car occupants and truck occupants wear their seatbelts in the same proportion. We gathered some data. We gathered some data from car people. We gathered some data from truck people. We ran a test. The test said that the probability of our sample data being what it was is about a 1.6. Right? We are going to reject the null as long as our alpha level, our possibility of making a mistake, is 10% or less. We're at a 1.6% chance of making a mistake here, of rejecting the null when we shouldn't, so we're going to reject. We say that there is enough evidence to reject the claim. Right? The chance of this happening randomly and being that far out there on that tail, pretty small. Now, I do want to point out something. I chose passenger cars as 1 and trucks as 2. If you had chosen those the other way around, that is, if you made passenger cars all your 2s and your trucks 1s, your setup would look mostly the same. Your p-value would be the same. The only thing that would be different would be that test statistic. Instead of a 2.4, you would get a negative 2.4. The reason being is back here in the formula. If we switch all the 1s and 2s here, effectively these two guys change position, and these two guys change position, and nothing else changes about the formula, which mathematically would be the same as multiplying the whole thing by -1, which means we would get an opposite z-score. Instead of a far out there on the right tail, we get far out there on the left tail. Okay. Remember, a z-score of 2.41 means we're 2.4 standard deviations above the mean, a negative, which means we're below the mean. Right? The equals 2 problems are the only ones where that's going to be a thing, because how you define 1 and 2 for everything else is going to affect your hypotheses. Right. Let's take a look at a second example here and see if we can make some sense out of it too. All right, that one went pretty well, I feel, but let's hope this one goes as well too. All right, a medical research team conducted a study to test the effects of a cholesterol-reducing medication. At the end of the study, the researchers found that 4,700 randomly selected subjects who took the medication and 301 the researchers found that of the 4,700 randomly selected subjects who took the medication, 301 died of heart disease. And of the 4,300 randomly selected subjects who took the placebo, 357 died of heart disease. At a significance level of 0.01, can you conclude that the death rate due to heart disease is lower for those who took the medication than for those who took the placebo? Okay. I'm going to start the same place I started the last problem. And it's something we didn't have to worry about in 8, but we worry about in 9. There's 2 groups. Which one's 1 and which one's 2? All right. I do it, again, how they show up. There's the first data that I have, so that's going to be group 1. There's the second data I have, so I'm going to call that group 2. So if you took the meds, you're group 1. If you took the placebo, you're group 2. Right? Let's look at the claim now. The claim is that the death rate is lower for those who took the medication than those who took the placebo. That the death rate, which we're going to call our P1, is lower for those who took the medication than those who took the placebo. Are we good with what we're seeing there? Let's turn that into a pair of hypotheses. Now, by saying lower, we're saying a strict inequality, which makes that our alternate, and that our null is just that P1 is equal to P2. Technically greater than or equal to, but the way this text, the way the homework, the way the tests are written, it's just equal to. I'm not going to get into it. It makes me nuts, but it is what it is, and I follow the game. Okay, I need data. I need data about group 1, and I need data about group 2. Now, what I learned from the last problem is what I really need is an x1 and an n1, an x2 and an n2, and an alpha level. I'm lazy. I'll do the easy thing first. Alpha level, 0.01. X1 and N1 is group 1 data, so that's going to be 4,700 for our N1 and 301 for our X1. N2 is going to be 4,300 and X2 is going to be 357. I don't have P hats for either group, but honestly, I don't care. I don't need them. Okay? I think I've got everything I need. I've got X's and N's and X's and N's and an alpha level. I've got a hypothesis. Yeah, okay. Let's run the test. So my test will be a 2 proportion z-test. X1 is 301. N1 is 4,700. X2 is 357. N2 is 4,300. And I want P1 to be less than P2 for my alternate hypothesis, so I'll select that. and then I'll ask it to calculate. It calculates. I got a z, a negative 3.5, essentially. I've got a p-value. Look at that p-value. What does that say? It says the p-value is 0.0003. Remember, scientific notation, so a p-value of 2.75 times 10 to the negative fourth. We'll move it 4 places to the left, so that's 3 leading zeros. The 2.7 turns into a 3 when rounded, so we got an extremely small p-value. So I'm going to compare the p-value to the alpha. P is much smaller than alpha, so that means we will reject the null. Remember, the claim, though, was the alternate, right? If the claim is the alternate and we're rejecting the null, then we would say that there is enough evidence, sufficient evidence to support our claim. So there is sufficient evidence to support the claim that, and what was the claim? Oh yeah, the claim was that the death rate was lower for the drug. That's good. So in terms of this is a statistical test, and assuming this is somewhat realistic, I know that we adapted this from the New England Journal of Medicine, so we simplified it a little bit. But basically we said that, hey, if you took this drug, you have a reduced risk of death from coronary disease, from heart disease. So I think you should take this drug if you're concerned about your heart. Okay? Okay, so now, a question that I'm sure at least one person has. What if they had said P2 was P1 and P1 was P2? Okay, really quickly. Your claim would be that P2 is less than P1. Right? Your hypotheses would be that P1 is greater than P2. Okay? For whatever reason, we always write it 1, 2, so you'd have to flip the direction of this guy. Your null would still be the same, that P1 is equal to P2. When you ran your test, you would just flip-flop all the data, meaning this would be 357, this would be 4,300, this would be 301, this would be 4,700. Okay? You'd select that guy, because you're doing that. You run the test, but you notice that how the z-score just went from negative to positive? Our test statistic was negative 3.4 before. Now it's positive 3.4. But look at our p-value. It's the same number. Our p-values are the same number. And that's okay. That's how it should be. So even if you flip-flop the groups, some of this might look a little different. Your final answer is still going to be the same. All right, I'm going to end this video here. We're at 23 minutes. We'll come back and do a couple more examples in part 2. See you for that.